Okay, so this is going to be the last lecture of this course. We'll call it summary. So we'll go lecture by lecture through whatever we have done, just to recap. So we started this course, which is called Applied Computational Fluid Dynamics. This was, well, it says applied, but that's just one part of the other, which says computational fluid dynamics, right? So CFD, that is what we discussed in this course. I gave you a quick introduction, the course policy, and we'll come back to that later to see if we have fulfilled the learning outcomes of this course. Then we moved on to talking about what are the pros and cons of CFD, and we realized that yes, computational fluid dynamics is a useful tool that we can use to solve fluid mechanics and related equations. So then I gave you one common form of the equation, which we call the general transport equation. Okay, so we have a common form, and in this course what we strive towards was to learn how to deal with this form of an equation that we are solving. Right, so this common form of the equation, if you want to chat, you can chat after the class or outside. Okay. So the common form is what we have been, or what we strive to solve, and we were able to achieve that goal. So the common form had four main terms. This is called the general transport theorem, transport equation. So there are in fact full-fledged courses on transport phenomena. You'll have books which are written on transport phenomena. Okay. So these are transport of mass, momentum, energy, and even other scalar quantities. So it has four terms in it. I'll write the equation because it's the equation that we have been trying to solve. So there is a transient term, there is a convection term, there is a diffusion term, and there is a source term. And I believe most of us feel confident to be able to solve equations of this kind, right? Right, so this contains the mass transport. Well, I mean, mass transport can be written in this form: momentum transport, and even energy transport. In fact, the heat conduction equation, transient and steady state that we talked about, it's nothing but energy transport. In containing only conduction. You can also have convection terms, but we to discuss convection terms, we actually moved on to the full fluid mechanics momentum equations. Okay. Well, then we talked about the ideas of problems being well posed. Basically, the reason we discussed about well posedness was to talk about the need for initial and boundary conditions. Without them, you cannot solve the problem. In fact, if you change them, the solution changes drastically. And that is what you may have realized in your labs and assignments while writing programs. It's very important to be able to implement those conditions correctly, and if you change them, the solution changes. And that is what typically happens, right? I mean, physical phenomena which is modeled using mass, momentum, and energy is still the same for everything, for all cases. What changes is only the boundary and initial conditions and the domain. A domain is basically a way to say we are changing boundary conditions. The equations are still the same every time, right? So these are, it's very important to understand what are the correct boundary conditions to use. This is typically done in more engineering and physics based course, but in a computational course like this, we learn how to implement them and solve the problem. Don't close the door. There may be other people coming after you as well. Right? Then we summarize the overall solution strategy of computational fluid dynamics as a three-step approach. One is pre-processing, followed by a solver or processing, and then you have post-processing. So in a typical program that you have written, you may have noticed that we defined delta x, delta y, delta t. That's a part of pre-processing. So you assumed the mesh to be Cartesian, nice rectangles. So that was your choice. So you have chosen a mesh. Based on that, you have indexing I comma j in the equations. Then you also decided what boundary conditions to use, what initial conditions to use. So that was all a part of pre-processing. Then came solver, where you had to solve the equations, and that typically takes the most amount of time in terms of computational expenditure in your problem. So there you solve the problem, you run iterations, you run loops, and so on and so forth until you converge to the solution you want. And so that is solver. And once you have the solution, which is typically in the form of arrays, data structures in the memory, or you may have dumped that into text files or binary files. Now you have to understand, visualize, and extract useful information out of it. So that is called post-processing. Okay, so we have learned how to do all parts of this, but mostly this course was about learning how to implement solvers, because that is the most trickiest part. Otherwise, it's mostly trivial. Okay. Good. Next, this lecture number 4 was simply talking about some equations that we were going to deal with this in this course. Then we classified the equations into 3 parts or 3 types based on the behavior of solution. So one was elliptic, the other was parabolic, and the third was hyperbolic. And that was important because the course was, I think 75% of the course was split into discussing these. So basically the course was 25% elliptic, 25% parabolic, 25% hyperbolic, and the last 25% combine them into the fluid mechanics equations. Okay, so this lecture was mainly about classifying the equations, and then we started with the idea of finite difference methods. So we started with the elliptic equation, which was Laplacian of phi equal to 0, and here, through every step we learned skills which were common in CFD, not only specific to elliptic equations. So the first was to discretize the domain. So we have to write the equation in terms of unknowns, and the more the number of unknowns, you can get a better accuracy. That's the whole idea of CFD, right? If you have more computational resource, you can do things in a much more accurate way, but then you need more time, computationally speaking, to solve it. So we learned about the idea of discretization, and we learned about first order derivative or derivatives of various orders. So this is the typical finite difference approach. We talked about forward difference, backward difference, center difference, and a very important idea called truncation error. Because errors are very important to understand in computational fluid dynamics. So I'll write as a summary of a finite difference method, and here you learned about the idea of truncation error. So when you write the Taylor series expansion and you truncate terms, you approximate derivatives. You have partial differential equations, so you have to approximate derivatives in terms of discrete values, and that results in a system of linear equations. So once you discretize discretization of the governing differential equation results in a linear system of the type of Ax equal to p, where x is the list of unknowns that you have to solve for, which is basically 5 values at the different nodes in the domain. Needs to download these things. Right, we learned also how to find the order of accuracy of a given scheme. That was given to you as problems in quiz as well as your midsem exams. I think you've learned how to find the order of accuracy of a given scheme. In fact, we also learned the other way around. So we learned how to use a certain number of points and come up with schemes. That is something, I mean, if you don't need to remember these schemes, although you'll always have textbooks and texts available, but you can quickly come up and derive these. If I give you 3 points to come up with a scheme for a given derivative, you can easily do that using the ideas we have discussed. Okay, so we learn about these finite differences, so to say, and then we moved on to apply this at for solving elliptic equation, and we started simple. So we started with one spatial dimension, no time. It's elliptic, so there's no time. So we started with only one spatial dimension. So that results in d2 theta by dx2 is equal to 0. So this is where we learned, in fact it was not 0, we had source terms as well. So this was the equation that you had. So you had an equation which involved a source term as well. And then we had boundary conditions. So we learned how to implement that for elliptic equation first. So this resulted in an equation, a linear equation of this form. And what we noticed was particularly the tri-diagonal nature of the matrix here. And this allowed us to use the tri-diagonal matrix algorithm, TDMA, which is nothing but applying the Gauss elimination to this particular form of the matrix, which results in an algorithm which is quite simple. And we learned about that. You also implemented that as a part of your labs. So you notice that storage wise it is much efficient, because all you have to store is just 3 arrays in the matrix, rather than having an n square storage. You only have to store n times 3 amount of storage, and that storage does not increase during the process of applying Gaussian elimination. So that's the reason TDMA is efficient. Okay. Next was when we moved to parabolic problems. That was when you have a transient term available as well. And when we have the transient term available, then the solution nature changes and the method should also get modified. So first we talked about the idea of explicit approaches that results in a stencil which looks like this. So explicit approaches are where you solve for an unknown in terms of all known values. It's very easy to implement computationally. I'm sure everybody appreciates that after solving assignments and labs using explicit approaches. It's very easy to implement computationally. Okay, but the problem with explicit approach is that it has issues with stability. Right? We noticed that not in this lecture, but a bit later, that these schemes. Well, this was just applying the okay. So we talked about implicit approach as well, where we get a matrix system again, and then we can solve it. But every time you solve this TDMA, you get the solution for next time step. So there's another variable, time here. So you have to do this TDMA again and again and again for as many time steps as you have in your problem. Okay, that's the only difference. We also talked about other schemes like Crank-Nicholson, which is order delta x um, squared as compared to the previous ones that we have seen. So it gives better accuracy, but of course the stencil is more dense. So you have more number of points in the matrix, so more work is required. And there's also a way to specify general theta schemes that we have talked about, and you will see in solvers, rather than saying backward time center backward time backward time center space and schemes like this, what they'll have is they'll have a general theta scheme. So you have to, or eta scheme, whatever. So you'll have to set a value of eta, and changing the value of eta will result in different kinds of schemes that you are using. And that's when we moved on to, sorry, I think I missed. Selection 8. Yeah, no, this is done. Lecture number 10. Right, so that's when we moved on to the problem of stability, or the issue of stability. So stability is where most of the issues come with explicit scheme, that there is some parameter that has to be constrained. In this case, it was a numerical Fourier number which has to be less than half, and that puts a condition on your time step or mesh size. So if you want to control the mesh size, you have a particular spatial accuracy requirement that results in a very stringent delta t. So then you have, if you want to move to a certain time, then you have to keep very small time steps. So lots of time steps will be required. That may result in you reaching that particular time after a few days or after a few months sometimes. So for very accurate solutions to problems which include dynamics of fluid dynamics around aeroplanes, where you want really accurate results, that takes sometimes months or more to solve one problem. So that's the amount of commitment we are talking about. Okay, with explicit scheme, that becomes an issue. And then if you want to control your delta t, let's say you want to keep delta t large, that means you have to keep your delta x large as well. Again, your spatial accuracy will suffer. So that's a problem with, and this is a major problem with explicit schemes. Okay, so this is one choice one has to make while solving a problem, explicit or implicit. So explicit has an issue with So we talked about, this general idea, but to learn how to find or analyze stability of a given scheme, we talked about the von Neumann stability analysis. So I'll not discuss that analysis here today. I'm sure you have got enough practice of that through problems that have been given to you as part of assignments as well as midsim. So this lecture was all about the von Neumann analysis. The next one as well, again. So as long as your mod g, which is the ratio of the magnitude of your Fourier wave at n plus 1th time divided by an, the mod of that has to be less than 1. The errors should not grow for any k value. Even if for 1 k value it starts increasing, chances are that your solution may diverge, because typically you will have some contribution for almost all wave numbers. Okay. Right, we also talked about transient 2D heat conduction, only a one spatial dimension more, but that resulted in a major problem that TDMA cannot be used because you have a banded matrix like this. And also this results in, if you want to work with one index, you lose the idea of elegance of having a double index, because your space is in 2 dimensions. You cannot use I, j. So that is where we introduce iterative methods to you. That was a major point in this course, of discussion on iterative methods. Okay. So we talked about the Jacobi method and then a slightly improved Gauss-Seidel method. But the whole idea of this was that you start with some guess value of the unknowns and then you improve them using an iterative formula. That's pretty much it. Okay. I'm sure you've been applying that so many times that it's become a second nature now. So Jacobi, an improved method called Gauss-Seidel. We talked about the idea of residuals, and talking in terms of residuals helps us because as the solution approaches the correct value, then residuals tend to 0. Okay. There's a lecture 14 missing. I think we could record it. Okay. So lecture 15 was where we talked about diagonal dominance, learned about the idea of boundary conditions, higher order boundary conditions sometimes resulting in the lack of diagonal dominance. So one has to be careful with the use of boundary conditions. And one way to get past that is to use under relaxation. So if you use under relaxation, that in a way is elevating your central coefficient, and that results in diagonal dominance in the algorithm. Okay, so that's one way to get rid of these conditions. The other way is to use fictitious points, which results in boundary condition, higher order boundary condition formulations, which are in fact diagonally dominant. Okay, so the convergence of these iterative methods was also one idea that we talked about, because that's important. You should have confidence in the fact that your iterations will converge. Next, we talked about improving these methods. So we talked about symmetric SOR, SOR with lines, block iterative methods like ADI, alternate direction implicit. I'll not go into details of all these things, but they are just improvements in iterative method. You can revise them yourself. Alternate direction explicit is what we talked about as well. We talked about something called a hopscotch method. Okay, so these were methods that were discussed. Just download. Right, so ADE, hopscotch, and coloring schemes are typically used in parallel solvers where you have alternate points that you solve using different processors. Right. So after having a very good discussion about iterative techniques, we moved on to hyperbolic equations. And just remember, in CFD, hyperbolic equations cause problems in general. In fact, it is sometimes said that first order derivatives create issues. Second order derivatives in general are good. First order derivatives can cause problems. So first order derivatives in convection. Diffusion is second order. Good. Convection can cause issues. Okay. So we have, hyperbolic equations was discussed separately. Although we didn't go into much of a detail, there are in fact books written on CFD, but only dealing with hyperbolic equation. And mostly that is what you'll get stuck with. And if you think about heat transfer, what is a major mode of heat transfer in general? Convection, right? Convection. If you want to have heating in a room, you would definitely have some sort of a blower working. Radiative heaters are there, yes, but convection is the major mode of heat transfer. Conduction if there's no wind moving, air moving at all, then the heat transfer is really slow. So in general, convection, engineering wise, that convection term is important. I mean, what is fluid mechanics without the convection term, right? Will have a convection term. You're solving for u, so u is there. So that's the trickiest part. So if you get stuck, you'll want to read books on hyperbolic equations. Well, hyperbolic equations are more than just this. Wave equations also fall into this category, but fluid mechanics wise, this is going to be a major issue. Okay, so this requires more reading if you want to stay in the field. Anyway, so we started with the 1D wave equation because that's closest to the kind of equations that we have. In fact, the governing differential equation that we wrote or that we learned to solve is a special form of the transport equation. Okay? And the major idea we learned here was upwinding. That was completely new to us. So depending on the direction of wind or velocity, we will decide which terms or how to discretize terms in the convection term. Okay, so that was the major idea in this. So let's write hyperbolic equations, and here the major idea was upwinding. Sorry, 19. Well, then we took a break, or we changed gears and talked about modified equation. I'm sure most of you are scared with this equation, but it's very useful. So if you have to derive, I gave you a couple of problems, right? So make sure you have tried deriving the modified equation for those problems. I cannot be any more helpful. Okay, so please make sure you are able to, for Richardson's scheme, I think that was given in the class, maybe in the next lecture. So make sure that you are able to derive modified equation using the steps. If you need help, then the book by Chung, that's already shared in the Moodle server, that has a good discussion on modified equation. In fact, I got my notes from there. So please, they have certain questions and problems, and they have given modified equations for schemes. So make sure you go through it and learn. Try to derive modified equation for any one equation, any one problem that's given. If you're able to do it, you should be able to do well. Right, so what does modified equation help with? 3 things. First, truncation error, because it allows, it will help you figure out if there's any cancellation going on between time and space terms in terms of truncation errors. Second, stability, very important. And third, the nature of solution, whether it's dissipative or dispersive. Okay. So these 3 things. Good. So that was 20 lectures. Well, this was again dispersive errors, and then we felt confident to move on to fluid mechanics, fluid flow equations. We talked about fluid flow equations. And particularly for incompressible flows. Because engineering wise speaking, mostly, especially in mechanical engineering, you deal with situations where the flow can be considered incompressible. Mach number less than 0.3, it can be, even air can be considered incompressible. So, and actually computation, CFD wise, solving incompressible equations is more complicated than solving compressible flow equations. So it's even more important to talk about the difficult ones, because compressible ones are much easier. And why is that? Why is incompressible, solving incompressible flow equations difficult? Because not density but pressure. So pressure, there is no explicit equation for pressure, but pressure appears in your velocity equations. So indirectly, the pressure equation is derived through the continuity equation, right? So first, what we did was we tried to get away with this using the vorticity stream function approach. We said that let's get rid of pressure altogether. So we ran away from that problem by talking about the vorticity stream function approach, and there we learned how to derive the vorticity equation. And interestingly, vorticity equation was also like the transport equation, right? It had the same form as it had a convection term where the phi got replaced with omega. It had the conduction, diffusion term and transient term. So all terms were there. There was no source term, right? There was no source term here. And then the stream function equation was again very similar to just a diffusion equation with a source term, a Poisson equation. So we were easily able to solve it. And at this point, we also introduced the finite volume approach to U. All right. So I'm slowly, recapping the last 4 months here. And then we got a bit stuck or confused with implementing the boundary condition. We as in like not me in the class, but in general, dealing with boundary conditions for this is confusing because there's no natural boundary condition for omega or psi. Natural, not mathematically, but natural like intuitively. Because we had to come up with ways to get boundary conditions for omega and psi using omega written in terms of psi and so on, especially on the walls. It was quite problematic, and that in fact is the reason why we do not work with these variables. That is the reason most of the solvers only work with your primitive variables u, v and p, even though dealing with this becomes much easy computation. Because implementing boundary conditions becomes quite confusing. In fact, when you would have worked with solving the lid-driven cavity, applying the top boundary condition would have been a bit tricky. Now, top boundary is like streamline, right? But if you consider all of them streamlines, then where do you introduce the idea of u equal to u not on the top boundary? So you see that you have to figure out sort of hacks to implement boundary conditions with these. So that is the reason, because of these this problem and others, the other major problem is it only works for 2D, doesn't work for 3D flows. So then we moved on to full 3D solvers. So first we talked about the semi-explicit method here. I'm not opening lecture notes for these things because these are very recent. So we don't want to recap great details of those. So semi-explicit, where all the terms were discretized at the nth time. Then we talked about the semi-implicit. And then finally, implicit. And that was quite intense, and that was where we sort of ended this course. Okay. So if you look at the summary, it's not a great deal of content that we have covered, although we went into details. So that's the reason the summary could be discussed in a couple of pages. But the whole idea is that this is the major amount of content we have covered. Just a couple of other things. So there's one thing that we never discussed, explicitly, was something called an advection diffusion equation. So this is actually the equation that is the common form that we have written. Okay. Del by del t of rho phi plus divergence of rho u phi is equal to divergence of so this is called the advection diffusion equation. So we solved an equation which had these two terms, the transient heat conduction equation. We solved an equation which had these two terms, the 1D wave equation, and we solved an equation which had, we also solved an equation which had these two terms, the Poisson equation, and we solved an equation which had this, and this for fluid mechanics. But where the phi was actually velocity, that was a bit more complicated than having phi being a scalar. But you may have situations where you are dealing with transport of, let's say, concentration. So there, or convection in heat convection. So there you will have these terms where phi will not be velocity. That's a bit easier to solve, right? Because u is already available to you. You simply have to implement the terms. But there what happens is that now you have both convection and diffusion terms. So you have to figure out how to discretize them. So when you read more literature or when you work with these equations, you read about something called a Peclet number, okay, which gives us a ratio of the prominence of convection to conduction. It's not a computational idea, it's more of a physical idea, that it's a ratio of convection to conduction. So if you have more convection than conduction, convection dominant flows, you will have higher Peclet numbers. So there you have to make sure that your upwinding is taken care of. But if you have situations where conduction is dominating, velocities are really small or ratio wise. So there in fact you can work with center difference even in convection terms. Because the information transfer because of conduction, diffusion, is actually much more prominent than convection. So these ideas are something we did not discuss, but there are books that do talk about it. But using the ideas discussed in this course, you can understand these ideas. So this is an equation that we did not explicitly talk about in this course. The other was unstructured grids. Now we worked with nicely Cartesian grids, but in commercial software or open source codes, you saw that they were using triangles or triangulated grids or tetrahedrals in 3D. And in reality, we work with unstructured grids in practice. The reason is because complex boundaries can easily be taken care of. Okay. And you saw that mesh adaptivity, you have these really elongated grids and so on. So with Cartesian, that becomes a problem. Okay. So we did not talk about how to deal mathematically with these grids. So that is some sort of a challenge when you work with, and that when you deal with unstructured grids, that results that generates or discussion on new discretizations that involve these unstructured grids. And in finite volume method, mostly the issue is to figure out how to come up with approximations for boundary fluxes or for boundary values in terms of nearby points. So you will when you read advanced literature, you'll see the different, not as simple as saying that phi at E minus phi at P divided by delta X, that only works with Cartesian homogeneous grids. But if you go to unstructured grids, there are some different techniques available. So that is something we did not discuss as a part of this course, but when you read literature, you will start making sense easily. Okay, and as I said, we did not talk about compressible flow equations, because in compressible flow equations, the pressure actually is written in terms of density using the gas laws or some sort of material laws. So pressure, you're not solving for pressure, you're solving for density, and you have an equation for density that's called the continuity equation, because you have a del rho by del T plus del dot U dot grad rho equal to 0, right? Oh, sorry, let's write in a conservative form. For those who have learned about compressible equations, and that's easy because now you are solving for a quantity rho, so we can use our explicit the idea of transient equations that we have learned, this is very similar to your 1D wave equation, right? That's pretty much what it was. And you have learned how to solve it. So you have three unknowns, rho, u, and v, let's say in 2D, and you have three equations for them. It's much easier. There's no predator-corrector approach required at all. Okay, so we did not discuss about it for these reasons. So that was pretty much what this course was about. And as promised, we did have demonstrations. So we demonstrated ANSYS Fluent, we demonstrated OpenFOAM, and we demonstrated a finite element code as well to demonstrate some ideas of unstructured grids and so on called fluidity. So we learned, we saw how realistically problems are solved using these software. Well, open source codes are a bit more non-intuitive at first to handle as compared to commercial codes like ANSYS, because of course a lot of time and money has gone into development of commercial codes, so that they are definitely user friendly as compared to these codes. But once you get used to open source, they are actually they can be more comfortable for those who have been working with them for a long time. And then you can do very interesting things like writing scripts and automating tasks and so on. And we also promised you to teach you how to implement these equations. And typically that is where the gap lies. Many people who have done CFD courses, similar courses, can't even write a line of code. Especially the ones who have learned CFD from this applied approach. But we should be, because if you excel in CFD, there are two job avenues open to you. One is a CFD developer and one is an application engineer. So in a CFD development job, well, there's no development without coding. And an application engineer, you have to interact with developers. You talk to the client, that is what they want, and you talk to the developer that this is what. So if you don't understand that language that the developer is talking, you'll not be able to communicate or bridge. So we gave you a brief understanding of writing programs using a very simple language called Python. And realistically, you'll have codes written in C, C++, Fortran, these kind of slightly lower level languages as compared to Python. But the idea was conveyed. So if you have to learn, or if you look at a CFD code or a module or a project, you will start making sense much easier than if you had not learned any programming as a part of this course. Okay, so the labs and assignments, associated assignments 1 and 2, were there not to torture you, but to teach you how to write CFD programs. Right? So that's the end of this discussion on the course.